Since we have a parametric form for circles, then that's going to mean we're going to have a parametric form for circles' close cousin, which is the ellipse. Now, the standard form of an ellipse, which you should have seen in pre-calculus or algebra class, is x minus h squared over a squared plus y minus k squared over b squared is equal to r squared. So that's the standard form for an ellipse. So it's sort of like a circle because it has a center and it has, well, it doesn't really have a radius. It has an axis, a major axis and a minor axis. We'll get there. All right, so let's eliminate the parameter for this problem to find a description equation of the following arc in terms of x. Well, we kind of know it's going to be an ellipse, but let's prove it. Okay, so I'm going to take this, I'm going to eliminate the parameter. So that means I'm going to solve this for t. So that would mean x plus 3 equals 2 sine t, which would mean x plus 3 over 2 is sine of t, which means t is the arc sine of x plus 3 over 2. All right, well now I'm going to take that, I'm going to plug it into this other equation right here. And so y is equal to 4 cosine of the arc sine of x plus 3 over 2 plus 5. Now, you might have remembered, you've seen problems like this, I don't know, probably in pre-calculus trigonometry class. You don't need to find this angle. I mean, you don't know what angle this is, but you can find the cosine of this angle, right? So this is some angle. So let's draw a little triangle for ourselves. Hopefully a little less wobbly than the one I just drew. It's a little wobbly. I'm just going to kind of figure this out. All right, so we have some angle theta. I know that theta has a sine that is x plus 3 over 2. So that means that I know that its opposite is x plus 3, and I know that the hypotenuse is 2. If I want to find the cosine, I'm going to need to know this side right here, right? Because cosine is adjacent over hypotenuse. So I'm going to have to use the Pythagorean theorem. Well, it's the Pythagorean identity, which is that a squared plus x plus 3 squared is equal to 2 squared, right, which is the hypotenuse squared. I'm going to solve this for a. I guess I should have put that in blue too. Sorry about that. So that's 2 also, right? There we go. All right, and this is 2 squared. Okay, so that would mean that a squared is equal to 4 take away x plus 3 squared. So a, this side over here, is the square root of 4 minus x plus 3 squared. Right? We just assume positive because, well, when you do arc sine and cosine, it has to be quadrant 1. All right, so then the cosine of theta, right, this angle, which is what I'm really looking for, right? I want the cosine of this angle. So if I call this angle theta, right, I want the cosine of that angle. Sorry, that's a theta. All right, so the cosine of theta is the square root of 4 minus x plus 3 squared divided by 2. And that's what we'll go substitute in. So all of this is kind of on the side. Work that we're doing on the side to help ourselves over here. So this will be equal to 4 times, and instead of cosine of all of that stuff, we will put in the square root of 4 minus x plus 3 squared over 2 plus 5. So that means that y is 2 times the square root of 4 minus x plus 3 squared plus 5. All right, well, that's all well and good. I mean, technically I've eliminated the parameter, but this is terrible, right? So this is an explicit equation, but it's not very good. So, and then of course we kind of fudged the whole plus or minus thing. So anyway, what if I square both sides, right? What if I subtract 5, so y minus 5 is equal to 2 times the square root of 4 minus x plus 3 squared. So that means that y minus 5, I could have just done it over, well, I'll do it this way, equals the square root of 4 minus x plus 3 squared. Well, now I can square both sides. Now I can just say, here, I'll pick a different color. Now I can just square this, and I'll have y minus 5 squared over 4 equals 4 minus x plus 3 squared. So if I add this to the other side, x plus 3 squared plus y minus 5 squared over 4 is equal to 4. Hello there. That's the standard rectangular form for an ellipse. I guess I should have put that. Standard rectangular form. Right? Because it's x and y. So, hello, standard rectangular form. All right, so we eliminated the parameters. We found the equation. The equation is an ellipse, right? It's an ellipse, which we kind of knew anyway because I labeled it that way at the start of the page, but nevertheless. All right, now the major axis and the minor axis. The major axis is whichever one's the longer axis, and the minor axis is the smaller axis. So my major axis is actually going to be x equals -3. And it's going to have a half length. I mean, it would be a radius, but the problem is that it's not consistent all the way through. So a half length would be equal to 4. And the minor axis is y equals 5, and it has a half length equal to 2. Right? Oh, I know why. If you're wondering where the 4 comes from, let me just help you out a little bit. Actually, I'll make it easier. We'll just look at the graph in Desmos, and that'll help. Right here. Isn't it beautiful? Okay, so you can see this is that graph that we were looking at. So it's 2 sine of t minus 3, 4 cosine of t plus 5. And again, I've thrown in that little trick just because I like to watch it get drawn. And if I look at the rectangular equation we just came up with, there it is. So your major axis is your long axis. It goes from, it's at x equals -3. It goes from the top of the ellipse to the bottom of the ellipse, right? And the half length, think of it sort of like the radius, it's the distance from the center out to either the top or the bottom. So in this case, it's 4. The minor axis in this case is the horizontal axis because it's the shorter of the two axes. And so it'll be at y equals 5 because, of course, your center is at -3, 5. So one way or another, your axes were going to be x equals -3 and y equals 5. It's just a question of which one's major and which one's minor. So your center is at -3, 5 for sure. Another way to write the form of this particular one would have been to say x plus 3 squared over 4 plus y minus 5 squared over 16 equals 1. That's kind of actually the more standard form, is to set it equal to 1. And when you do that, you could say or this, then it matches the patterns that we have written down from pre-calculus. This is on your conic sections reference sheet, but it's from pre-calculus. So we have a vertical major axis, and so it looks like this. And so our major axis vertices are k plus a and k minus a, right? So the vertices, if we look at the ellipse for a second, k being 5, right? So it's at 5 plus 4, 5 minus 4. Therefore, the vertical axis is at x equals -3, and then it's 4 wide, right? So it's getting its -3 coming from the x portion, but then it's getting its 4 coming from the 16, if you want to see it that way, right? The square root of 16 is 4. And then the square root of 4 is 2, and therefore the minor axis is at a half length of 2. Now, if you're thinking, hey, this might lead us to another standard issue way of looking at parametric equations for ellipses, just like we did for circles, well, you would be correct. So we have a general parametric equation for an ellipse. It's right here. So if your horizontal axis is radius A, your vertical axis is radius B, your center is at HK. We're assuming both of those are positive. Then let's look at cosine, A cosine t plus H, B sine of t plus K. And there we have it. So we're looking at a standard parametric ellipse right here. So we have a cosine t plus h, b sine of t plus k. And as you see it get drawn, it seems very similar to a circle, right? So it starts at the right and it moves counterclockwise, which I'm writing down on my sheet, but I'll go back and show you. Before I go any further, though, let's look at a couple things. So later on in the box, it asks us what happens if we change the sign of A and B, and it can alter the starting point. So if I let A be negative, it makes it start over on the left. If I let A be positive, it starts over on the right. So it can change where it graphs. Same thing with B. If I let B be negative versus B be positive, it'll change the orientation. So that's that comment in the box right here. It says changing the signs of A and B can alter the starting point and or the direction of the orientation. Enjoy the Desmos graphs. The most common one we use, however, is just like you think. It starts at the right and it goes this way. Moves counterclockwise. The major axis is whichever axis is longer. And then the shorter axis is the minor axis. It'll be half the length. So the axes are going to be A and B. It's just a question of which one will be which. So we don't know which of A and B are longer or shorter. So one of these will be A and then the other one will be B. So we'll just say half length, which is sort of the radius, but not quite, because radius is always consistent. These are not. So half length of the axes are either A or B. All right, sine and cosine is also valid, but just like with the circle, when you make it start at sine and cosine, so let me turn this one off, let me turn on the sine. So when you do that, it starts at the top and it moves clockwise, just like it did for a circle. And of course, it looks very circular right now, and that's because I'm making it so that the A and the B are very similar. If I make them exactly the same, then you have a circle. Right? And a circle is like a special type of ellipse. A circle is an ellipse where the axes are the same because the radius is consistent. Right? All right, so this would be starting at the top and it moves clockwise. And of course, as always, you're welcome to go play with that Desmos graph, which is available to you to figure out, how A and B alter things and so on.